In the past, we've briefly touched on the fact that strong acids produce more ions than weak acids, and weak bases produce more ions than strong bases. In this lesson, we're going to get into the mathematics behind that, and we're going to look at conjugate acids and bases and conjugate bases and acids and see how they're related. There's going to be several math problems that I work throughout this, so you can feel free to skip around, but I will talk about every slide, sometimes more than others. So, just a quick review. Strength is the extent to which acids or bases ionize in aqueous solutions. The more ions they produce, the stronger they are. So if we look at a generic reaction, which is just a generic acid, A for acid, when it reacts with water, it produces H3O+, and the conjugate base A-. And a strong acid yields 100% of hydronium. That means all of this thing ionizes, and we get lots and lots of H3O+ and lots of A-, and this is really just a one-way reaction in a strong acid. If it's weak, then it is both directions, as these things reach a dynamic equilibrium and the acid-base keep transferring back and forth, and we do end up with this in some amount in our final product. So weak acids only produce small amounts of hydronium ion because some of it remains HA, some of it remains the acid. Bases have a similar thing. We'll get to those in a minute. But we can actually measure and determine the strength of an acid and a base by measuring its equilibrium constant in an aqueous solution. Remember, an equilibrium constant is just the reaction quotient at equilibrium. So that's the concentration of reactants divided by the concentration of products, but we don't include solids or liquids in the quotient, so because water is a liquid and it's the solvent, I mean it has no concentration, that doesn't make sense, we ignore it. So basically the Ka value, or the acid ionization constant, the equilibrium constant for an acid, is given by the concentration of hydronium times the concentration of the conjugate base divided by the concentration of the acid. This is all at equilibrium. And so as you can see, if we have a stronger acid, this is going to be a bigger number. This is going to be a bigger number because stronger acids produce more ions, and they do that at the expense of the initial acid. So that's going to be a smaller number. And when we make the denominator little and the numerator big, the whole number gets big. That means the bigger the Ka value, the bigger or stronger the acid. Now, these are the Ka values for some acids, and you'll notice that for the strong acids, I don't even have numbers here, they're just large. And if you think about it, it's because a strong acid 100% ionizes, which means there is no HA left at equilibrium, right? In this reaction, we have some concentration of HA. Well, if it's a strong acid, it's 100% ionization. This is 0, and dividing by 0 doesn't make sense. So I don't put a number here, it's just really, really big. It approaches infinity, it's big. Okay? Now, hydronium ion, H3O+, which is our definition of acid, does have a Ka value. It's equal to 1, which means when we start dealing with our weak acids, we're going to expect fairly small numbers. So you can see that these all have powers of times 10 to the negative something. So all the way down over here, where we have water, it's got 1 times 10 to the negative 14th, doesn't surprise us, and hydronium ion is 1. So that's the whole pH scale from hydronium to water. Now, percent ionization, I mentioned this. This is a different way for talking about the strength of an acid. It's basically just how much acid or hydronium ion we get compared to how much acid we started with. And you got to be careful with this because this is not an equilibrium value. This is the value at before the reaction occurs. So we can actually get a percent ionization for a strong acid because we put in whatever this, and all of it ionizes. So basically, if we put in 1 mole of HA, of 1 mole of strong acid, then we're going to get 1 mole of H3O+ divided by 1 mole of what we started with, and that's equal to 1, and we multiply by 100 to make it a percent, we get 100%. So the percent ionization is not a super complicated thing, but you do have to be careful because it's a quotient of an equilibrium and an initial, not two equilibrium concentrations. Calculate the percent ionization of a 0.125 molar solution of nitrous acid with a pH of 2.09. Alright, so pH tells me the concentration of hydronium, right? Remember, P means the negative log, so pH is equal to the negative log of the concentration of H3O+. And since the inverse of this is 10 to the negative log of H3O+, that is equal to the concentration of H3O+. That is the reminder that 10 to the negative pH of something is equal to the concentration of H3O+. So if I want to do this, all I have to do is take my initial concentration of the nitrous acid, 0.125, that's my denominator, and I have 10 to the negative 2.09, that's my concentration of hydroxide, and then I can divide 10 raised to the negative 2.09 by 0.125 and get and multiply that by 100, right, to make it a percent, and I get 6.5%. So 6.5% of nitrous acid ionizes, the other 93.5% doesn't. It actually remains HA, and so this is a weak acid since it does not produce very many hydronium ions in water. Bases, like I've been saying, the same rule applies to those. We can measure and rank base strength based off of the ionization constant for the base, which is found in a similar fashion. We start with a base, it reacts with water, and from that we get the conjugate acid and hydroxide ions. So to get the reaction, or the acid, to get the base ionization constant of Kb, we just simply multiply the concentration of the conjugate acid and hydroxide divided by the initial, or the equilibrium concentration of the base. So these are all equilibrium values. Again, water is the solvent, we don't include it, so the percent ionization is found in a similar fashion. We find how much of it actually ionized divided by how much of it we put in there, multiplied by 100, and we get our percent ionization. So if you can do it for an acid, you can do it for a base. We just got to remember bases produce hydroxide, not hydronium. Everything else basically stays the same. Now, if we put the two things together, we get a little bit more of an interesting result. It allows us to relate Ka and Kb for a conjugate acid and its base, or a base and its conjugate acid, however you want to look at it. So I have my generic reactions written for an acid, HA, this is my acid. It reacts with water, it produces hydronium, and its conjugate base, A-. Well, this same reaction is then happening in reverse, and so that's what I have here, the conjugate base reacting with water, which produces hydroxide and its conjugate acid. And for an acid, we can find the Ka value, and for the base, we can find the Kb value. So it says summing the equation yields the autoionization of water. And when I say summing these equations, all I'm doing is I'm adding all these things up. So it's like I'm carrying out both reactions simultaneously. So I take HA and H2O, these two guys, and they're here, and with that I'm going to put in its conjugate base and more water, and that's these guys here. So I've put the two reactant sides together, and I've got the two product sides over here. Now when I do that, I can actually find the ionization constant of whatever this thing is, or the equilibrium constant for this thing. And so we're going to look at that, but first let's simplify this reaction because it's nasty, right? But I can simplify it if things appear on both sides. So this is HA as an aqueous thing, and that's also a product over here, so I can cross out HA, I can cross out HA. H2O appears on the left, but nowhere on the right, so I've got to leave it there. A- appears on the left and on the right, so I can cross out those. And so H2O plus H2O, so I have two H2Os, and they are producing, I have H3O plus and OH minus. Okay, so what you can see is when I have an acid and its conjugate base reacting together, I basically just have the autoionization of water, the acid and base part goes away. And this is handy because if we take these two things together, we can actually figure out the relationship of Ka and Kb. Because if we find the equilibrium constant for this big long reaction, which I'll go ahead and do, remember that's the product of the concentration of the products, so concentration of H3O plus times the concentration of A minus times the concentration of OH minus times the concentration of HA divided by the concentration of the reactant side, that would be HA, and we don't include water, so then we just have concentration of A minus. Now let's look at this. We can simplify it, but before we do, this H3O plus times A minus divided by HA, that's this, that's Ka. So right here I have Ka times, and this right here, OH minus HA over A minus, that's Kb. Okay? So Basically, when we sum these things together, their equilibrium constant is the product of Ka and Kb. But if we simplify this HA cancels that HA, this A minus cancels that A minus, and we have this, and so this thing is water, and its equilibrium constant is Kw, right? Because it's H3O plus times OH minus, which means the ionization, autoionization of water is equal to the Ka value times the Kb value, or the acid ion constant, and the base ion constant. So this is an important relationship. Kw equals Ka times Kb. Now, if you think about this, Kw is a constant value, right? It's always 1.0 times 10 to the negative 14th. That means there's an inverse relationship between Ka and Kb. So if this number is big, this number has to be little. That means if my acid is strong, the conjugate base is weak. And if the acid is weak, the conjugate base is strong. And that's an important thing to remember. And it's going to be something that we will use. We will use this relationship quite a bit. So keep that in mind. The stronger the acid, the weaker its conjugate base. The stronger the base, the weaker the conjugate acid. But Kb times Ka is always equal to Kw for an acid and its conjugate base. Now, this table actually shows that relationship fairly nicely. We've got acids over here, stronger acids at the top, bases over here, and these are the conjugate bases, and so stronger bases at the bottom. So you can see HClO4, which is a very strong acid, it undergoes complete acid ionization in water. So 100% ionizes. Its conjugate base is the ClO4 minus, the perchlorate ion. But it can't attract protons because water is actually a stronger base than it, which means if this thing actually pulled a proton, water would be like, I get it back, and it would pull that proton back to it. So these things, the conjugate bases of the strong acids, they don't actually act like bases in water. They're just an ion. They're a salt. They're just floating around, and we don't have to worry about them having any basic properties. The same is true for the conjugate acids of strong bases. They do not undergo acid ionization in water. They don't donate protons. So the strong bases, their conjugate acids actually don't act like acids in water. So we don't have to worry about those. But if we have things that are somewhere in between, if we have weak acids and weak bases, then their conjugates actually do act like acids and bases in water, and we have to keep track of that. So we're going to look at a couple example problems where we use these relationships. It's really not too bad, you just got to keep track of what's happening. So an example problem here is given that the equilibrium constant, the base ionization constant of nitrite ion is NO2 minus is 2.17 times 10 to the negative 11th. Determine the Ka for its conjugate acid, nitrous acid, or HNO2. So this is not hard at all. Ka times Kb equals Kw. Hardest part about this is remembering that Kw is equal to 1.0 times 10 to the negative 14th. So all we're going to do is solve for Ka. Ka equals Kw divided by Kb, so 1.0 times 10 to the negative 14th divided by 2.17 times 10 to the negative 11th gets us 4.6 times 10 to the negative 4. Another example problem, determine the relative strength of the acids NH4 plus and HCN by comparing their ionization constants. And it's not uncommon that we can look up Ka and Kb, but sometimes we only have Kas or we only have Kbs. And here we're only given the Ka of HCN. NH3, we are given a Kb. Well, why would we be given the Kb of NH3? Well, let's think about the acid NH4. The acid NH4 plus, when it reacts with water, water's H2O, it produces, and this is go both directions, it produces NH3 and that proton which joins with water H3O+. So what we actually see is this acid has the conjugate base ammonia NH3. So this is our conjugate base, which means because we know Kb, we can find the Ka of its conjugate acid. So really all we have to do is say the Ka is equal to 1.0 times 10 to the negative 14th divided by this Kb, 1.8 times 10 to the negative 5th. And that gets us 5.6 times 10 to the negative 10th. And so it's a close thing. This is 4.9 times 10 to the negative 6 for HCN. This is 5.6 for NH4. So NH4 plus is just a little bit stronger, not a lot, but about 0.07 times 10 to the negative 10th times more. So NH4 is a slightly stronger acid than HCN. All right, so quick summary here. We know that weak acids, when they dissolve in water, they produce some ions, but some of it actually stays as the compound HA, and so it's going to have a fairly small Ka value, and we can calculate that using this equation, because remember 10 to the negative pH is equal to the concentration of hydronium ions. Similarly, with weak bases, they also don't completely ionize, which means we get some hydroxide, we get some of the conjugate acid, and we end up with mostly the initial base still in non-ionized form floating around in solution. So here's an example problem. This one gives us a bunch of values, and it just asks us to calculate the Kb value for caffeine. So remember, Kb is going to be equal to the concentration of hydroxide, OH minus, times the concentration of conjugate acid, so Hb plus, divided by the concentration of our initial base. And they actually tell us all this in the problem. It says we have determined the Kb value for this, and the concentration that we started, or that we have of the base, is equal to 0.05. The concentration of the conjugate acid is 5 times 10 to the negative third, and the concentration of hydroxide is 2.5 times 10 to the negative third. And we get 2.5 times 10 to the negative fourth. Now this next example is a little bit more complicated. It says determine the Ka of HNO2 if a 0.0516 molar solution has a pH of 2.34. And the reason this is more complicated is it doesn't tell us this is all at equilibrium. We make a solution of nitrous acid by making a 0.0516 molar solution, and then we stick a pH sensor in there and we measure its pH, and it's 2.34, and we're supposed to determine the Ka value. To do this, we need to know what's happening. So HNO2 is reacting with water, H2O, and that produces NO2 minus, the conjugate base, and H3O plus. Now, how much of this does it actually make? Well, we don't know. We have to figure that out. But we do know that we started with an initial concentration of 0.0516 molar nitrous acid. This is our solvent. We don't care, so I'm just going to draw an arrow. And then we have 0 of this initially, and essentially 0 H3O plus. It's not actually 0 because water auto-ionizes, but 1.0 times 10 to the negative 7th is insignificant compared to our initial concentration of acid, so we don't worry about it, and in this class we never will. Okay. Now the change, since this is a one-to-one stoichiometric relationship, we're going to have plus x here, plus x here, and minus x here, which means at equilibrium we have a concentration of 0.0516 minus x, x, and x. Okay, so it looks like we might be out of luck and we can't actually find Ka. We do know that Ka is equal to the concentration of H3O plus, that is x, times the concentration of NO2 minus, that is x, divided by the concentration of HNO2 at equilibrium, so 0.0516 minus x. So we need to know x in order to solve this. Well, remember, x is equal to the concentration of H3O plus. And since we know the pH value, all we have to do is take 10 to the negative pH, and we have that number. So x is equal to 10 to the negative 2.34, which is simply 0.0046. And if we plug that number in for x, so we square that, and then we divide it by 0.0516 minus 0.0046, we get 4.4 times 10 to the negative fourth. Okay.